Hello, good morning everyone. Am I audible?
Yes, sir.
Okay. I think we'll start. Already some 24 are there. Start. Let me present the screen. Yeah. Is the screen visible to you?
Yes, sir.
Okay. So last class we were discussing about non-uniform quantization. We discussed about mu-law compounding. Basically, we use this term compression. Actually, it is compression. But since compression and expanding used together at the transmitter, compression is used, and receiver we have expanding. So that's why it is called as compounding. Okay. Otherwise, it is called as compressor at the transmitter. So we discussed also that if you use non-uniform quantizer with mu-law compression, this mu-law compression is used in North American standards. And this is, if we use this non-uniform quantization, the prediction towards practical SNR will be better compared to uniform quantization. That's what we discussed. And we said that we'll use ALA compression also, but other standards. Okay, so mu-law compression is used in North American standard. And we have ALA compression, which is used in European standards. So that I quickly write that ALA compression. So ALA is called as ALA, and the European standard they use. So mu-law is used in North American standards. North American standards for quantization purposes. Okay. So now ALA compression is used in European standards. And this characteristics is going to be Z of X, similar to mu-law. Okay, A mod of X divided by 1 plus log of A, where X is between 0 to 1 by A, and the characteristics are different if X is between 1 by A to 1. So this characteristics will be 1 plus log of A of mod of X divided by 1 plus log of A. So this is the characteristics of Z of X. So remember, we had an equation. Why did we derive Z of X? We wanted to find out, so here you can see that Kz we wanted to be far less than 1. Then only the noise with non-uniform quantizer is less than the uniform quantizer. Uniform quantizer, when you derive the SQNR, the quantization noise was del square by 2. That is with uniform quantizer. Now we have a compounding factor Kz, which is far less than 1. To make that Kz far less than 1, we had some parameters here to consider. We wanted this Kz far less than 1. Then what should be Z dash of X? Kz and Z of X are related to inverse square. And when Z of X is far greater than 1, then we had all these parameters. Okay, so I think we have seen which function will give us the parameter. Okay, so Z dash of X and Z of X. You can see that if Y is equal to, so let me put this here. So we wanted Z dash of X far greater than 1 because we wanted this Kz to be far less than 1. So if Z of X has to be far greater than 1 means X has to be far less than 1, mod of X has to be far less than 1. And if X is approximately equal to 1, then Z dash of X is far less than 1. So which function is going to give us these values is, we had looked at log, but natural logarithm function at 0 it is minus infinity, value is minus infinity at 0. This function will not satisfy this log characteristic. So we wanted some characteristics which is X greater than 0, it should be log of X. Minus log minus X is X less than 0. So the compression law, which is approximately follow this characteristics, whatever we wanted is modified. Now this natural logarithm, whatever is that, it been shifted 1 plus mu of X divided by ln of 1 plus mu, then sigma of X. So we had a characteristics which is called compression characteristics out of this. And now in ALA also it is same way. but the values are different. The VA value is different. So here mu value, as I told you, it can vary from 1 to 255. Maximum value is 255 here in Mueller, but A value is different. And now Z dash of X would be Z dash of X is going to be, if you differentiate this with respect to X, it is 1 plus log A for X between 1 by A, 0 to 1 by A. Then if you differentiate this, again the value of X is from 1 by A to 1, it is 1 plus A, okay, into mod of X. So if we differentiate this parameter, so it will be 1 plus A into mod of X, and this is varying between 1 by A to 1. So these are the characteristics of Z dash of X, which is going to give us the compression characteristics of something like this. Okay, so we'll plot mu law and A law. So no compression means you have all the uniform step size for all the amplitude levels. Compression means you are assigning more values for the lower amplitudes and less values for the higher amplitudes. Okay, less quantization levels for the higher amplitudes. So now this A value is going to vary from 1 to 100. Normally A will be taken as 88. Okay, practically they found out 88 A value will give us the good compression characteristics. So they are plotted both A law and mu law.
So what's the A mod X, sir? A mod X is a function. Yeah.
Yeah. So this is in mu law we have defined this characteristics, right? Z of X. So this Z of X is basically, so we have this input. X is going to be input actually. X is going to be input and Z of X is output. So this characteristics when we plot, this characteristics, output versus input when we plot it, okay, the characteristics, the curve with compression is Z of X and X is going to be the input. X is going to be the input and Z of X is what we are plotting, compression characteristics. Same way in A law also, here it is, X is going to be mod of that input, compression characteristics of A law. Let me take out the characteristics. It will be, let me plot it, okay, so that it will be more clear to you. Just hold on. And the compression characteristics for A law and mu law, I'll just show it to you. So now you can see that it's plotted. A law and mu law are plotted like this. So now the notations are little different. So don't worry about the notations. Here, M is going to be the input. There, X was going to be the input. That's all. There's nothing else. Normalized input is M. There it was X was a normalized input in the equation. So here this is output was V. There output is Z of X. Here again output is E. One is A law. First one is mu law. Second one is A law. So you can see that as mu is equal to 0, it is basically uniform quantizer. So this mu is equal to A, whatever we have got, mu is equal to 0. Okay, so this is uniform quantizer. This part, this is uniform quantizer. Okay, so mu is equal to 5, mu is equal to 100. It is a compression characteristics according to Mueller characteristics what we have derived. So this as mu increases, the compression characteristics you can see it is not neither logarithmic not linear. So you can see it is having the equation. It is having the equation of here. You can see that Z of X is ln of mu X, ln of 1 plus mu signum of X. So it is neither logarithmic nor linear, but some regions it is linear, some regions it is logarithmic. It's a combination of that. So that's what is depicted in the figure. Mu is equal to 100, mu is equal to 250. 250 means it will again, it will become like this. So again, it will start a characteristic something like this. So mu is equal to 255 means it will be something like this. So this will be same mu is equal to 250, maximum value. Now A is equal to 100 is maximum value in A law, and A is equal to 88 or 87.5, okay, is the characteristics of something is equal to 88 or 87.5. Sorry, this is A. A is equal to 88 or 87. So practically they found that A value of 88 will give us a good characteristics. Okay, A is equal to 88 and mu is equal to 255. These two values are used, and this is used in North American standard, and this is used in European standard, and we follow North American standard. Okay, so this is about compression characteristics. Now let us. This is actually the entire process of sampling, quantizing, and encoding. Sampling and quantization, and encoding. Encoding is basically assigning the binary code to the levels of quantizations. So this entire process is called as pulse code modulation, PCM, pulse code modulation. So let us look that into great details in today's class. Okay. So is this clear to you? The compression loss, ELA and MULA, different standards are there. Different countries they follow this, different standards. And sampling, quantization, and encoding is called as pulse code modulation. Okay. So is this clear to you?
Yes, sir.
Okay. So now this is a block diagram of a uniform PCM. When I say uniform PCM and non-uniform PCM, here non-uniform quantization is used. So here non-uniform quantization is used. That is the only difference. Okay. So you can see that here uniform quantization is used. Otherwise all the blocks are same. Uniform quantization is used. You can see that PCM means we have a sampling, we have a quantizing. The encoder is basically different levels are other than different code words. If there are 8 levels, 0 to 7, 0, 0, 0, 0, 1, 1, okay, 1, 0, 0, like that. From 0 to 1, 1, 1, all the levels are used. In non-uniform quantization, you can see you have a compressor characteristics, G of X, which we have derived. Either it will be ELA or VLA, depends on the standard. Then we use uniform quantization. Then we encode and transmit. Actually, there is one more block here, encoder. After that, it is transmitted through the channel. This is channel. After it is passed through a channel, we have a decoder because we have done the encoding here. Then we have done the compression at this point. We need to do the expansion. Okay, so G inverse of X is expanded. Then we use a reconstruction filter. This may be low pass filter, which is going to attenuate all the high frequency components, and we get the output here. Okay, so we'll get back estimate of X of N. So X of N estimate will be getting at the receiver. Okay, so now let us quickly take out the block diagram, detailed block diagram of PCM system. Then we can look into that in more details. So actually we have discussed, we are putting them together. So this is basically PCM block diagram. We are putting them together actually. So now we have discussed sampling separately, quantization separately. Encoding is basically assigning the values to different quantization levels. So now we can see analog source of message signal is there. So this could be, as I told you, it could be data, it could be video or voice or multimedia signal, whatever it is. And that is pulse amplitude modulated. This is basically sampling. So flat top sampling we have learned now. So this is basically flat top sampling. Okay, flat top sampling. So let me write it outside so that it will be. This is basically a flat top sampling. Flat top sampling. So we have understood how to use sample and hold circuit. I think MOSFET and other capacitor how to use with op-amp so that flat top sampling is obtained. That is that after the samples are obtained. So this signal is called as discrete time continuous amplitude signal after the sampling is obtained. Now you pass that through A to D converter. A to D converter actually has this PAM, but they have separated this out, okay, just to indicate that, okay, sampling is done. Later, this analog digital converter has got two jobs. One is quantization, then encoding. So both will be done in the analog digital converter block. Then it is passed through the channel, digitally encoded message signal. This is all ones and zeros. 1 0 1 1 1 0 0 1 0, some digital message. Okay. So now this is what is PCM block diagram. At the receiver, it is D to A conversion is done. That is, if you use a non-uniform quantizer, so compression is used here. You use expander here, then take out the samples, and this is again demodulator. So quantization, now you use a demodulator to get back whatever you have sampled here. So this sampling rate is greater than 2 FM or equal to 2 FM, so that I can get back the information from the samples. So this is passed to the destination. So this is the basic block of PCM. So now first one is the sampling is done at the transmitter side first. The sampling is FS has to be greater than 2 FM for perfect reconstruction of the information from the samples. So in textbooks, what they'll do is they'll use a anti-aliasing filter, okay, at the transmitter before the sample. First block is so anti-aliasing filter. Let me call it as low pass. Okay, low pass anti-aliasing filter. So what this will do is, this will eliminate any high frequency components which are greater than FM. So FM, this is restricted to FM. So the cutoff frequency of this low pass filter is restricted to FM. Anything low pass anti-aliasing filter, any higher frequency components are eliminated. So the maximum frequency component is FM. After that, they pass it through a sampler. So here we do flat top sampling. Flat top sampling. So the sampling rate is fs is greater than equal to 2fm. So here I am going to get a sampled version of the signal. Sampled version. So if I use x of t here, I will be getting x of nts. Okay. So this is sampling. Basically, we have done this in detail. Now quantization, as we discussed earlier. So in uniform quantization or non-uniform quantization. So quantization at the transmitter. So sampling is done. Next is quantization is done at the transmitter. So what we have a message signal input m of t. Okay. So then we'll pass this message signal through a compressor. Okay. If we are going to use non-uniform quantization in practice, so compressor used. Then we pass this through uniform quantizer. Uniform quantizer. Then you have a compressed output signal. Compressed output signal. So this is a non-uniform quantization at the transmitter side we are going to use. So as we told, we are going to use A law and mu law. So if I use mu law, then the characteristics. Okay. So here the output is V. So this is output, that is Z of X in our notation. Then ln of 1 plus mu m. M is going to be the input. So don't get confused. There X was input. The notations will be different. Okay. But otherwise meaning is going to be same. Divided by ln of 1 plus mu. So this is what we are going to use as mu law. And m is input and v is output. So there should not be any confusion between m and v. Okay. So now we said that the characteristics are here. The same characteristics we are going to use. Okay. How this compression characteristics will vary with respect to input as well as with respect to values of mu and a. Okay. So let me the characteristics. Okay, so m and v are scaled. M and v are scaled up so that they are normalized to -1 and +1 only. M also is normalized to -1 and +1. V also is normalized to -1 +1. That's why the scale is 1 to 1. This maximum value is 1. Again, this value and that value is 1. In the interval -1 to +1. Now it is plotted for mu is equal to 0, 5, 11, 100. It can be plotted for 255. You can use this equation in MATLAB and give different values. The curve is going to look like this. And now for a given mu value, okay, for a given mu value, then we can find out the reciprocal, okay, slope of the compression curve. Okay, so we can find out the reciprocal slope of the compression curve. Then it is reciprocal sloping, so it is with respect to m divided by dv. Okay, reciprocal slope of the compression curve. How do you find out the slope? You differentiate. Okay, and this, if I differentiate this, it will be ln of 1 plus mu divided by mu into 1 plus mu of m. Okay, so this is the characteristics what we are getting. So now this is going to state that mu law is neither strictly linear nor strictly logarithmic. It is approximately linear at low frequency. Linear at low values, not low frequencies, low values. So low levels when mu of m is far less than 1. That means it is logarithmic. Okay, it is linear at low levels. Low levels means when the amplitude levels are low, this mu law is going to be linear. Okay, for mu of m is far less than 1, and it is logarithmic. Okay, logarithmic at high levels, that is higher amplitude levels. It is going to be logarithmic. So you can see that characteristics is this characteristic. If you see almost the small values, this till this point. Okay, say 0.5 or 0.5 something like that. If See the characteristics is almost linear. But if it is for higher amplitudes, we want lesser quantization levels. At that time, it behaves as a logarithmic function. Okay? So logarithmic at higher values of mu m is mod. Okay, is for greater than 1. Okay, so is this clear to you? Hello.
Yes, sir.
Then if you use ALA, again it is similar to what we have written. So V magnitude.
So can you please go a bit slow, sir?
Yeah, I'll go slow. So now V is for ALA, V is again output and M is input. So A mod of M divided by 1 plus ln of A 0 to 1 by A. And if it is 1 by A to...
And sir, I didn't understand the last one, sir. Linear at lower levels and logarithmic at high levels. How so?
Yeah, one second.
Okay. Yeah.
Yeah. Now we look at the equation. Characteristics. So if you look at the characteristics, okay, I think we have proved this also in the last class. Look at this when x is far less than 1. Here, x is far less than 1. X is far less than 1. Okay. So here this is x is far less than 1, mu is far greater than 1. I think from this we proved only compression characteristics here. When x is equal to 1, it was 1 by ln of 1 plus mu. If you have to find out that, you have to differentiate. That differentiation is done here. Differentiation is done. You can see now if x is mu of m, if it is far less than 1, okay, if mu of m is far less than 1, so this is basically 1, right?
Yeah.
So this part is basically 1. Okay, this part will be neglected. So this part, I think you can see that ln of 1 plus mu, if mu is lesser, then you can see that the characteristics are ln of mu. Any equation is there where it is approximately equal to mu, something like that? Maybe because not aware of.
There is.
Yeah. So that I'll maybe mathematical equation exactly I'm not aware, but I can come back to you. Let me revise that logarithmic rules. So that's why it will be linear characteristics only. That's why using that we can prove that it's a linear characteristics. And at higher values, it's greater than 1 means it is basically logarithmic only, it will follow. So using the equation as well as from the graph, it is very clear that for a lower amplitude levels, you see fix the value here at 0.5. So V is going to be 0.5. You can see that at this value, okay, this curve below this graph, it is almost linear, right? Approximately, not. I'm saying not
yes,
very clear.
It is linear. It is.
Yeah, it is. Yeah. But this here it is like, for lower values, if you consider only so much, it is approximately, you can take it as behavior as linear. So that way, from the graph, you can tell. Maybe logarithmic, I need to get back to you with the correct equation. I don't want to tell some wrong things. We'll get back.
With the graph, we are making the correct assumption, but the condition that we're writing is mu into mod m. That is the answer.
Yes. Mu into mod m means the message signal also lower value, and mu the function together mu as well as mod. It should be both together. When the value is low, the characteristics both will follow here now. So now consider mu is equal to 5. Mu is equal to 5. Consider mu is low, and this you consider 0.2 m together. If you plot a graph, okay, so I'll get a point here, right? So this point, if I get, and if I observe this characteristic from here to here to the origin, it will be linear only.
Yeah.
So that is about this. And even a mu is far greater than 1, it is logarithm at higher values. So now if you want to find out from the A law characteristics, again the reciprocal you need to take if you want to find out the slope characteristics. So it is differentiate with respect to V dm by dv. Okay. So now it is 1 plus ln of A divided by A all these characteristics are, all these equations we are writing for understanding purpose only. You don't have to remember all these things. Only definition of A law, mu law is sufficient. Differentiation you can do it on your own. So you don't have to remember anything here. ln of A into mod of mu. Then this is from 1 by A to m less than 1. So you can see this this characteristics also. It will be almost for lower level of A. A is 100, you can't tell that law. It will be logarithmic at lower value of mu also. For A is greater than say some more than 5 or something like that. But A for lower value of A is equal to 1, 2, 3 till 5, and for lower value of mu it will be linear. Otherwise it will be logarithmic. So we can, from the characteristics as well as from the equation, we can understand these characteristics. Okay. So this is about compression at the transmitter. At the receiver,
Can you show the A law graph, sir?
Yes.
So here we're not adding any equation, sir.
Equation we are writing. This is the equation.
We have written dou m by dou v, but are we writing any relation for the condition where we have linear and logarithmic?
Yeah. You can same equation you can write here. Okay.
Same equation.
Yeah, same equation. Instead of A mu, it will be A. And here you can see from the graph, for A value lesser 2 and 1, say A is till 5, okay, till A value of 5, okay, and mu m less than, lesser, okay, 0.2, 0.4, something like that, then still it will be linear only. Otherwise it will become logarithmic. If A is increased, it will become logarithmic. Okay. So now, it is compression is used at the transmitter side. So now the compressor signal we take compressor signal and we use that. Okay, compressor signal will take compressor signal. Expander, then we get a uniformly quantized version of the original message signal. So this is uniformly quantized version of the original signal. Remember, first we use compression, then we pass it to uniform quantizer. Now we are doing expanding, so we are getting back the uniform quantized original signal m of t. M of t is what we had passed here. So you can see now m of t is passed through the compressor, then uniform quantizer. Compressor signal is passed to expander. So we are removing the compression, we are getting back the uniform quantizer of m of t. Okay. So now practically, as I told you, mu is 255 and this is 88 is A value. Now encoding. So these 3 steps is basically PCM, pulse code modulation.
So what will be the output of the expander? Uniformly quantized signal, right?
Yeah, uniformly quantized, yes. Because in the block diagram we wrote here, so let me come back to that. Here we wrote so compression, uniform quantizer, pass through the channel. At the receiver, characteristics and expander characteristics are, you can see the characteristics. So you can see inverse characteristics. So we have compression characteristics here. Expand exactly about this. So we'll get back the uniform quantized
signal.
Yes. So yeah, encoding is basically, now we have discrete, after quantizer, what we have? Output of the quantizer. The quantizer is discrete amplitude. Quantizer is discrete amplitudes, discrete time, discrete amplitude and discrete time signal. This is output of the quantizer. Now we need to pass this through an encoder block, so which will assign code to the particular quantization level. So now what coding schemes are used again? Okay, so usually practically they use binary codes. Okay, all ones and zeros only. Again, how to combine that ones and zeros, that is different topic as it is, but binary codes are used in practice. So we'll be getting 101101100001, something like this. Okay, so preferred choice for the encoding is binary code, because the why they use binary code is, the advantage of binary code is the effect of noise encountered in communication system. Okay, so is lesser if you use binary code technique. Okay, so effect of noise, whatever we encountered in digital communication or analog communication, this binary code is more immune. Digital signal. It is more immune to the noise compared to the analog signal. So it is, and also it is easy to regenerate. Okay. So binary code advantage is immunity over noise, immunity over AWG noise, also easy to regenerate. That's why we use binary codes. Again, there are variations of binary codes. How to combine them, okay? How to encode them, how to add the redundancy, because this comes under channel coding. We add some redundancy so that probability of error of the receiver is reduced, even though it is getting affected by noise. So how to add those redundancies, that is again a separate topic for discussion. We will discuss at least one code in the syllabus, that is called block codes, in the last unit of your syllabus. Okay. Right now, let us understand. Okay, binary codes are used. So if you have 8 quantization levels, in the 8 codes are assigned, starting from 00 to 111. 111. Okay. So next, let us go for another coding scheme. Okay. So this is PCM is one type of coding technique, how to convert from analog signal to digital signal. Okay. So now let me go for another type of coding, which is called as differential PCM. BPCM, we call it as BPCM. Let me take out the block diagram of BPCM. Yeah. So let us discuss BPCM. So in PCM, we have studied, I take samples, then I quantize. Each sample is quantized. Now, in DPCM, instead of quantizing each sample, we call it as DPCM, differential PCM. In PCM, what we do, we take each sample, we quantize it to some level. Each sample is quantized to some level. But in DPCM, we take the difference between samples. The difference is quantized. And also, we have to understand one more thing here. In PCM, the sampling, whatever we have done in PCM, so here it is, sampling is done exactly Fs equal to 2Fm or Fs greater than 2Fm. Okay, so this is the condition what we have used for sampling in PCM. Okay, in DPCM, we intentionally oversample the signal. Oversampling is carried out. That is, Fs is far greater than 2Fm. Oversampling is done intentionally. Now tell me, if oversampling is done, then will the correlation between the samples, is it better or worst if oversampling is done?
It's better.
It's better, right? That means by looking at the samples of the signals, okay, if I do the oversampling at the transmitter side, I can relate. Okay, if I know the samples to a certain time interval, I can predict the next few samples at least, if the correlation between the samples are good.
Yes, sir.
So by oversampling, what we are doing, we are sampling at a greater than 2Fm, far greater than 2Fm. By doing this oversampling, we are able to achieve the more correlation between the samples. So if I know samples to some extent, then I can at least predict few samples next to the previous samples. So that is basically the principle of this next type of coding scheme, which is DPCM.
So, but even if you perform oversampling, you said that we use oversampling to predict what is going to happen in the next sample, right? Because of the high correlation factor.
Yes.
But if you predicted what is happening now properly, and you're trying to predict what is going to happen in the next sample, because of the correlation, you only know the part of the correlation which is what we already know. We still don't know the new part. So how does it help?
No, by knowing the current sample, can I predict the new sample? That is my question. It is possible, yes, because I know some correlation between the previous samples. I can tell.
You can tell what is going to happen in the new sample because the new sample is oversampled. But the new information will not be there with us, right? It's just the same information coming again and again because of oversampling.
No. The next samples, if I can predict, if the prediction error is smaller, then I can reduce the quantization error, right? Quantization error is still there in non-informed quantizer. Non-informed quantizer anyway, which is there, still the quantization error is still existing. We did not make it zero. Now what we are doing? Oversampling. Can I reduce that error?
Reduce the quantization error.
Yes. That's what it is. The main motivation for going for DPCM is there are some limitations. We'll come to the limitation of DPCM also. Every scheme has limitation. The advantage of DPCM over PCM is because of the oversampling, samples will be more, correlation between the samples will be more. By using this concept, can I predict the next few samples? If the prediction error is smaller, then the quantization error will be lesser. That is the concept. How can I reduce the quantization error? Further, compared to PCM. Okay. So now, if I take a voice signal or video signal or any data.
So can you show the block diagram? Can you explain the block diagram?
Yeah, coming to that. Because let me put some theory, then later I explain. In this class only we'll study this. Okay. So when you take a voice signal or any video signal, okay, or any data signal, data is basically WhatsApp message, SMS, whatever it is, it doesn't matter. So it is sampled at a rate which is greater than the Nyquist rate. That's what we are telling. So correlation between the samples are more, high degree of correlation will have, so that the samples will not change rapidly from one sample to sample because we have oversampled it, and that's why we can predict this next few samples at least from the previous samples. So this is basically DPCM, and here the quantization is not done sample wise. Here the difference between the adjacent samples are quantized. Difference between adjacent samples. Okay, adjacent samples are quantized. Not each sample is quantized. In PCM, each sample is quantized, and here since the difference is not much, so difference between the adjacent samples is quantized. Okay. So that's why it is called as DPCM. The name why it has come because of this nature. Let me erase this. So samples are quantized. Difference between the adjacent samples are quantized. That's why the name DPCM, differential pulse code modulation. Okay. So now the message signal M of t is going to be sampled at a rate Fs which is forward than 2fm, which is Fs is equal to 1 by Ts. To produce a sequence of correlated samples, the sample duration, okay, the Ts seconds apart will be there. Ts seconds apart, where Fs is forward than 2f. So that is known to us. Now, after sampling, what the signal we are getting? We are getting M of nTs. So now, let us take the block diagram. Now come back to the block diagram. So this is after we oversample the signal, we are getting a M of nTs. Okay. So now M of nTs is passed through a comparator. Comparator is basically here it is a summer, which is going to here where it is basically subtractor here. Okay, comparator is basically here taking the sample signal. It is the predicted version of that signal. Okay, predicted version of the quantized signal is coming here. That is getting subtracted from the original sample message signal. So this is a comparator. Then what is the error we are going to get? Actually, in practice, if the correlation is very high correlation between the samples, then the quantized value which is coming out of the predictor M hat of NTS and the sample version should give us 0 here when I subtract. But in practice, there will be some error because we are not going to predict exactly what will be the next sample observing the previous samples. So now we have M of NTS minus M hat of NTS, that is called as error, E of NTS. Now that is passed through the quantizer. Now the quantizer will have some error because it is not like a zero error quantizer. It will have some errors in quantizing. So those errors plus this E of NTS, whatever is coming, will be EQ of NTS. EQ of NTS is E of NTS plus the error due to the quantizer. That we'll write in mathematical equation now. The EQ of NTS is taken and it is encoded and we get a DPCM data sequence. The same EQ of NTS is getting added with the predictor filter output. The predictor filter output is getting added with the EQ of NTS to generate MQ of NTS. Then that MQ of NTS, okay, is passed through the predictor filter. That predicted output is M hat of NTS. So that we are again using. There is some feedback here. But look at the PCM. Any feedback was there in PCM? This system?
No, sir.
No feedback. So basically by adding this feedback, we are fine tuning this process. We are keep minimizing the quantization error. So here we have feedback loop. That is something going wrong here. This feedback loop is going to correct that. So here UQ of NTS is taken and its predictor output of the predictor also is getting added. You get a generate of MQ of NTS that is passed with the predictor output. That is M hat of NTS. Predictor output and the sample signal is compared again in the comparator. The error signal is obtained. Is actually we have to fine tune that. Using feedback we can fine tune this error. Error will become smaller. Okay. There are some limitations. We'll study as we go ahead. There are some limitations in implementation of this. We'll see what is the limitation of implementation. Let me take the block diagram of the transmitter again, and we can write the equations. Okay. So let me take this again and we'll write the equations. So let me take this here. Now let us write the equation. Let me remove this actually. The receiver is right now not required, only transmitter is required. Let me take only the transmitter part. Okay. Then we can go to the receiver later. Yeah. So this is the transmitter part, DPCM transmitted output. So we have M of NTS. So now let us write the equations. So this is sampled input, this is the predicted value. This is the predictor output. Predictor output. So now E of NTS, okay, E of NTS will be M of NTS from the diagram minus M hat of NTS. So this is the predicted value, this is the sample value, the error is going to be E of NTS. Let me call this as equation 1. Okay. So now the predicted value is produced by a filter. You can see in the block diagram, it is a prediction filter. What is there? Okay. The input is going to be the input to this is going to be quantized value of the error here, E of NTS. Okay, that will be the input, and also its own output of the predictor filter is again the addition of that is going to be the input for this. Okay. So the difference signal is going to be EQ of NTS here. That is, this signal EQ of NTS is E of NTS plus some quantization error, whatever is there. That will be EQ of NTS. That is getting added with the predictor value. That will be the input, the predictor filter. Okay. So now the predictor filter, okay, is if you have to look this into in details, okay, how it will be there, predictor filter. Okay. So it will be basically having some delay lines. So the simple way of implementing the prediction filter is basically we have to use a tapped delay line filter. So what will the prediction filter? So it will be consisting of delay line filters. A tapped delay line filter means it will be connected in a configuration. Okay, multiple taps are used or weights are used in a delay line filter, and or it is also called as discrete time filter. Discrete time filter. We can write the diagram for that also. So the delay, whatever is there, is set to sampling period. So delay of this filter is going to be set to sampling period. Now let us take that diagram and understand how the delay filter looks like in practice. Okay. So let me take this figure and put it here. So can you see this figure? Let me enlarge this. Yeah. So this is how delay line filter looks like. So the quantized input MQ of NTS is there. Look at the block diagram. Yeah. So this is MQ of NTS is the input to the prediction filter. The prediction filter is written here. So this is the prediction filter consists of some delay elements. So MQ of NTS quantized input is put here. It is delayed. We get MQ of NTS minus TS. Now we have weights here. These are called taps. Weights has to be found out. Some algorithm is there to find out weights. W1, W2, WP minus 1, WP. We are not going to discuss how to find out these weights here. Okay, there is some algorithm to find out these weights. So the weights are found out by an algorithm. Then this delay, whatever delayed version, is again multiplied. This is a multiplication operation. W1 is multiplied with MQ of NTS minus TS. Then again delayed, MQ of NTS minus 2TS, W2, multiply, add. So it is a summer here. It's basically multiplication and accumulation. So this summer is basically accumulating all these multiplication values. So it is basically multiply and accumulate. The first is multiplication is done. Next, Accumulation is done. Accumulation is done. So then you get a output of the predictor. This predictor output is better if you have more and more number of delay elements and more number of taps. More number of taps means more number of weights compared to as we have delay elements, we have weights also. Okay? So this is how it looks like. The predictor looks like this. Okay, it is having a delay elements. So now predictor output is m hat of NTS. That's what we are doing. Okay. So is this clear to you?
So are we going to go to the filter?
No, we are not going to go into the details of the filter. So these are weights, W1, W2, WP weights. It has to be computed using some algorithm. We don't have time to go to the details because again it is a topic to discuss on its own. It is a topic to discuss.
Okay, just one small question. On what basis are the weights chosen? You told us that you will not discuss the algorithm, but like intuition wise, how do we tune the weights at least so that we know what is the output of the filter?
Yeah. So weights are again it is based on some iterative manner. So I assume some weights initially. Okay. I assume some weights initially. Then I predict the value. So I have quantized MQ of NTS. I know what is the MQ of NTS. This MQ of NTS also has some information about M of NTS. Is it not? This MQ of NTS has some information about M of NTS.
It does.
It does because it is coming through this. Then we are getting this MQ of NTS. So now I assume some weights. Then I'll predict M hat of NTS. I'll compare M hat of NTS. Is it equal to or approximately equal to M of NTS? Because I know what is MQ of NTS. So then I have to choose if I choose more number of delay lines and more number of weight coefficient like this, then this prediction will be almost accurate. Okay. So it is done based on iteration. So there are some iterative algorithms are there. First choose the initialized weights, okay, to some value. Again, there is a procedure called diagonalization, eigenvalues, eigenvectors, all those things are there. There is an algorithm how to minimize this prediction error, which is called as minimum mean square estimate, MMSE, minimum mean square estimate. And there is one more algorithm called least square estimate. There are various algorithms to minimize the prediction error. So based on that algorithm it will be used. It's basically iteration only. It is an iteration process. Okay. Maybe if you choose an elective which is called as adaptive signal processing in higher semester, ASP.
Yes, sir. We're learning LSE, sir. We're learning.
You have DSP now.
Yeah, yes, sir.
You have DSP like that. You have ASP, adaptive signal processing. All these iterative algorithms will come there. It will be very interesting how to minimize the error and all this. So there are interesting topics you can learn when you go ahead in the subject. Okay. So as of now, okay, we are saying that okay, there is a predictor which is having some delay line filters. It is taking MQ of NTS. It is going to predict what is M hat of NTS. Our aim is to minimize E of NTS. That is our aim. Now the quantizer output. Look at the block diagram. Is EQ of NTS. I show you once again block diagram. The quantizer output is EQ of NTS. That is E of NTS plus the quantization error. EQ of NTS is E of NTS plus the quantization error. So we'll write that as E of NTS is the error plus some quantization error, that we call it as Q of NTS. Q of NTS is quantization error. And this is equation 2. Now this, let me call it as quantization error. Okay. Now the prediction filter input, that is MQ of NTS is the input of the prediction filter, that is M hat of NTS plus EQ of NTS. They are putting all the equations. So MQ of NTS, let me write prediction filter input. Prediction filter input is MQ of NTS is equal to M hat of NTS plus EQ of NTS. Okay, so this is equation 3. So you can look at this M hat of NTS plus EQ of NTS. So we are adding this, then that is the input of the prediction filter. Okay. So now let us use equation 2. Okay. So we have this equation 2 as EQ of NTS. Let us put this EQ of NTS in second term of equation 3. So equation 2 in
will the quantizer be an LTI system?
Quantizer is linear time invariant. It's a memoryless system.
Yeah.
Linear time invariant system. Yes.
So then, are we writing the equation the right way then? The second equation. We're just adding.
Yeah.
Just
So
adding it up.
Yeah, adding it out because here remember the sampling is at higher rate. So correlation is better. So that's why we're writing that. So actually, when you say linear time invariant system, here we want prediction. That's why we sample it a higher rate, higher sampling rate. We sample it a higher sampling rate because of that. So here I don't think so. After this, it is not an LTI system. After higher sampling rate, and also we said that we want the correlation between the sample is higher. So I'm predicting this means it won't be time in time. Yeah.
We have some information of the future.
Yeah, we have some. So at this point, we can't tell it is an LTI system.
Okay. Okay.
So equation 2 is substituted in equation 3. Equation 2 in 3. Let me. Pen is not working. Okay. So equation 2 is substituted in equation 3, and we are just writing mq of nts is equal to m hat of nts, just substituting that earlier equation. So it will be E of nts plus q of nts. So this is, let me call it as equation 4. Now we have one more equation, that is equation 1. So what was equation 1? Equation 1 was m of nts minus m hat of nts was equation 1. So using E of nts is m of nts minus m hat of nts. So from equation 1, mq of nts could be written as m hat of nts plus m of nts minus m hat of nts plus q of nts. So I'm just substituting this. So I'll get m of nts only because this will get cancelled, plus q of nts. So mq of nts will have m of nts plus the quantization error. So this is equation number 5. Okay. So if the prediction is good, then the average power of
So we can't hear you.
Signal power divided by quantization noise power. If the prediction is better, then the quantization error is lesser, then your SQNR is better, okay, compared to PCM. PCM is pulse code modulation.
So can you please repeat? So your voice got cut in the middle.
Yeah. So we want to say here that if the prediction is good, then the error is lesser. E of NTS is lesser if the prediction is good. Do you agree with that?
That's correct, so yeah.
Correct. So then the improvement over DPCM over PCM is, if the prediction is better, then signal to quantization noise ratio. If you find out SQNR, signal to quantization noise ratio, if the prediction is better, then this is lesser. So if this is lesser plus the quantization error, if you compute SQNR out of this, then the SQNR will be better with DPCM compared to PCM. That means the error is going to reduce. The mean square error, mean square error is going to reduce. The average error is going to reduce out of the quantizer because the prediction is better. So that way we can say that DPCM is better than PCM. We say that the average power of the prediction error E of NTS is smaller than the average power of M of NTS. So M of NTS, whatever you are getting here, the average power, that means the input signal power, input power. So the input power, if you compute out of this, and if you compute the error here, the prediction error, that is E of NTS. So if you compute the average power over here, so this average power will be lesser than the input power because the error is smaller. If the prediction is better, this error is smaller. This error is smaller than the input power. So if you find out SQNR, it's signal power by quantization noise power. So this noise power is lesser compared to this, the ratio will increase. So that way we can say that this quantization error is actually in the quantizer, we can adjust the number of levels so that this predictor will predict the input in a better manner so that the error is lesser. If error is lesser, the mean square error is still lesser. then we can say that SQNR is improved compared to feedback loop. The performance of DPCM is better than the PCM. In PCM, lower amplitude levels are quantized for more levels, and the higher amplitude levels are quantized with lesser levels. Only that we had, but we did not have an adjusting mechanism by looking at E of NTS. So if E of NTS is smaller, then the SQNR is better. If for some reason, if SQNR is getting worse, then I can adjust this number of levels over here so that I can pass it through a prediction filter. That prediction filter will be predicting this M of NTS in a better manner. Then I get a E of NTS lesser. So some adjusting mechanism is there, and feedback mechanism is there. So that quantization levels can be adjusted, depends upon the feedback, so that SQNR is better, okay, better than PCM.
So then the quantizer block is not DPCM but just a random generic quantizer.
Generic quantizer, but this is non-uniform quantizer only. But now these levels could be adjusted based on some input. Earlier, in the open loop configuration, if something goes wrong in a PCM, so here SQNR is getting worse. I can't do much about it because I don't have any correcting factor. Correcting mechanism is not there. But in DPCM, I have a correcting mechanism because I have a feedback loop where the prediction is there, and the quantization levels could be adjusted automatically to get E of NTS lesser. If E of NTS is lesser, that's all required for me.
Then to alter the quantization levels, we need a different quantizer, right? Because the previous quantizers were not able to.
No, same quantizer, but there was no feedback mechanism to correct that earlier. Now feedback mechanism is there, so I can correct this.
Okay.
Quantizer levels I can either increase or decrease based on the input. That input is coming from the prediction filter. If E of NTS is larger, SQNR is poorer. SQNR poor is not, not is of our interest. Our interest is SQNR should be better. So how will I know that? I know E of NTS. So how I get E of NTS? Because of the prediction only. So this feedback is going to tell me I need to improve or I need to stay constant.
Okay. And sir, how is it differential? I didn't
Differential, differential is
in the very beginning, sir.
Yeah, you can see that E of NTS is the difference between what? Sampled input.
But it's not from sample to sample. It's the difference between the sample that you have plus minus the prediction.
Prediction, correct. Now
but
here
not from sample to sample.
No. This quantizer is going to quantize this E of NTS. So now when the prediction is almost when prediction is accurate with respect to M of NTS, it is basically by knowing the earlier samples, you are predicting the next sample. So it is basically difference only is taken here. The previous sample and the next sample. Prediction is what predicting the next sample only, not like I'm predicting the 10th sample. I am predicting the second sample, third sample if I know the first sample. So if that error is lesser, then it is basically I'm taking a difference means I'm taking a difference between the sample. That difference in the samples is quantized, not the actual sample is quantized. Actual sample minus the predicted sample, that whatever difference comes, that I am going to sample. I am going to quantize.
Okay.
Okay, so I think we'll stop here. You will be losing the break. We'll continue this in the next class. We need to discuss the receiver block diagram. Then we'll be going for another modulation scheme, which is again a digital modulation, conversion scheme. Okay, conversion scheme. PCM is a analog to digital conversion scheme. DPCM is also analog to digital conversion scheme. But there is some limitation over here. We'll discuss what is that limitation. How to overcome that limitation, we'll be discussing in next class. That next class topic is delta modulation. Then we go for adaptive delta modulation. Then once we've done adaptive delta modulation, we'll go for delta sigma modulation or sigma delta modulation. So this is the, like we are evolving from PCM to DPCM to delta modulation to sigma delta modulation. Okay. So any doubts, others? Only one person or two people are asking doubts. Okay, if there are no further doubts, we'll stop here. Thank you. Thank you.
think. Okay, I think both the links are limiting us, the participants, to 100 itself. So what we'll do is we'll continue with B and D section now. For A and C section, I'll take the class again, say by afternoon or something. I'll inform and I'll let you know. Is that fine? Will that be fine? Am I clear?
Yes, sir.
Yes, sir.
Yeah, because I think both the links. One link was the free version, and one link was from the G Suite. Both are limiting it to 100. So what we'll do is we'll have a B and D section now, and then I'll inform over the WhatsApp what will be the class timings for A and C section. Okay, kindly cooperate, because nothing else we can do. Okay, for tomorrow I'll try to come up with a Cisco WebEx link which will allow more than 100 people.
Sir, you can turn on your mic in both the meetings and run parallel.
Shall we check that?
Yes, sir.
Let me try. Okay, let me try. But how can I connect to both the meetings? Can I?
Yes, sir.
Yes, sir, you
Have tried.
can.
Yes, sir, you can.
Yeah, I'll try. I am coming up to the other link. Yeah, I have done it. I think 33 people are already there. This is a better idea. If this works out fine. I think I have to present in both the places, right?
Yes, sir.
Just a minute. Yeah, I have around 100 here and I have 36. So, okay, let me check out. I have in one of the meeting 100 and one of the meeting 36, 37. It's increasing. I'll present in both the places. Hope all of you can see this slide.
Yes, sir.
Okay. I think the responses you'll have to little bit be careful about it. I'll just wait for a minute because in the other meeting there are some people still joining. Okay, it's eating up the time, but still. Okay, meanwhile, I'll just share the code of the data set. Okay, did you receive the thing? What do you say? The CSV file? All the people kindly download it. Okay, hope so. You have downloaded the slide. Sorry, CSV file. Now start off. We'll quickly do this, and then we'll go ahead with the further topics on it, kernel methods, etc. Okay. So yeah, where were we? Yeah. So yeah, you can see that if you want, but import pandas, import numpy, and import matplotlib. So in the first cell, do the import. Do these importations. Hope you are done with that. Yeah, still there are around 20 people missing in the class. Hope so both the meeting students are listening to me. And the slide is visible, just a single screen. Virupakshi from one meeting and Sai Pranav from one more meeting, kindly respond to me. Sai Pranav and Virupakshi.
So you're audible and screen is also visible.
Yeah, just for the confirmation of my side, from my side, okay? Don't take it any other way. Because, yeah, this side, Virupakshi. Is the screen visible and am I audible? Screen. Okay, okay. Import the NumPy, import pandas, read the CSV file. Do it quickly. Read the CSV file. Tell me the shape of the file, how much rows and how many columns are there. Don't open the CSV file. Do it from dot shape. Okay, and students, whoever were eligible, kindly apply for BE honors degree. You get a extra degree, no? Your seniors and all. Is it open for you or is it open for the 7th semester students? If it is open for you, kindly apply. No, don't. So you will have a degree before your fourth sem. You will have one more degree with you. Why do you want to lose on an opportunity? VTO is giving. Why don't take? Why don't you take it? All it requires, I think, an application and a little bit of fees or something like that. Okay, fine. So this one, what? So what is the size? Row and column. You can put it in all section if you want. Message or you can chat. Chat, you should be patient enough. Once I see, then only I can see. Then only I'll read it out. Yeah, some 1300 change cross five columns are there. Yeah, many of you got in both the meetings. Good. Okay. Yeah. What is this thing? If you do df.head, what are you getting? You're getting column names. Yeah. No. Are you getting the column names?
Yes, sir.
Okay. So this is not a direct numbers as we have seen in all the until now whatever CSV files you have seen, they were direct numbers, but this is not direct numbers. So there is some change in the data set. So there are 2-3 lines given in about the data set. I have taken it from a university. You say machine learning repository. So you can see, you can just go through. The link is there in the WhatsApp group. So just take 2 minutes and go through this thing and understand what is the data set. Data were extracted from the images that were taken from genuine and forged banknote-like specimens. For digitization, an industrial camera usually used for print inspection was used. The final images have 400 cross 400 pixels. Due to the object lens and distance to the investigated object, grayscale pictures with the resolution of 660 dpi were gained. Wavelet transform tool is used to extract features from images. So if you don't know about wavelet transform tool, just assume that it is a black box which extracts some features from the images, and that feature is the variance of the images, the skewness of the images, the kurtosis, the entropy, and the class. So we can consider a variance as x1, skewness as x2, kurtosis as x3, entropy as x4, and class as the output y. Okay, hope you are in the same line as I've discussed. So I've taken this bank data. Yeah, I hope you can see the screen. Did you put a screen? Okay. Can you understand what is this bank data drop doing?
Creating a feature set.
Feature set, but why is that class thing dropping? Am I dropping that class column?
We're dropping the class column from bank data to X, and then we retain the class column for Y. So basically, class is the output of the problem.
Yeah, so we are taking out the class, we are copying X with all the input features, X1, X2, X3. That is, as we have read in the repository thing, I think it is the variance, Q-ness, kurtosis, entropy into X. And only the class we are copying it to Y. So you can see there. Okay, a little bit of pre-processing, not too much. Okay, then you can use X-train split, train test split, X-train, X-test, Y-train, Y-test. So you can split. I've taken size to be as test size to be as 0.2. You can vary it. Okay, there's the cell which I've selected now. Hope everyone are there with me.
Yes, sir.
Yes, sir.
Yeah. Okay, kindly bear with the multiple feedbacks I'll ask. Yeah, where are they? Yeah. So X-test, X-train, Y-test, Y-train. This is the normal. Is this the holdout cross-validation technique? Or is it K-fold?
Holdout.
We are just holding this test size. We are keeping the model blind from the test size. Test data. So we are training it with one set of data, and we are unseen data. We are trying to test it. Okay, and then finally we have taken SVC classifier, SVM, scalar.svm. In that we have taken SVC classifier. In that the kernel is to be linear. Today we'll go through what is that kernel, and then we are fitting it. Okay, now everyone kindly do it with linear. Then you can change it with RBF. RBF is nothing but Gaussian, so you can change it with RBF and you can check, or polynomial and you can check. Okay, that you could do it at your leisure, but currently do it with linear. Okay, and then we are predicting it while we are fitting the model. We are using only X-train and Y-train. And while doing the prediction, we are using X-test. And then you have two things, confusion matrix and classification report. Okay, confusion matrix, classification report. Normal linear regression, it was model.summary. Here it is confusion matrix, classification report in classifiers. So you will get all the things which probably you have discussed in the class, the precision recall, accuracy. Put it in the chat window, whatever classification report you get. I think you can calculate the accuracy also like last class. Whatever we did, I think last class we did one more program. How did we calculate the accuracy? dot accuracy, right? Scikit only. I'm just copying that accuracy part from the previous class to this class. Hope it works. Else kindly do the required changes. SVM, you can type it like this. So this has to print three things for you: one confusion matrix, one classification report, and the last one is accuracy. Is there accuracy in the classification report? People who got it? Isn't there, right?
So accuracy is in there.
Yeah, isn't there?
Oh wait.
No, I think so. Because I think
sir.
precision, recall, F1 score, support.
Yeah, and along the indices you have accuracy, macro average, and weighted average.
What is the value?
So we get average for F1 score and support, not. I think it's the average of the all of the F1 scores for 0 and 1. It's not the average of.
Yeah, it is not the average. It is just the row average, column averages. So you can calculate the accuracy again. Anyhow, it is there on your screen.
Sir, we can do model dot score of X test comma Y test. That also returns.
What does it return? Does it return all the parameters or only the accuracy?
Only the accuracy. Model dot.
Only the accuracy. Yeah, you could do that. Yes. There are many ways. Okay. Hope you people have got some output. If you have got an error, kindly let us know.
0.985.
0.9898.
Sir?
Yeah?
CM.diagonal from which library, sir?
Which one, ma? Come again?
Diagonal.
Yeah, there. CM.diagonal. That is again from confusion matrix only. That yesterday, you're from ANC section, right?
Yes, sir.
Yeah, that was from confusion matrix which we took. Scalar na dot matrix. I'll do that. You can see it here, but anyhow, I'll do that. Yeah, I should have done that. A confusion
Dot
matrix is there,
diagonal.
no?
So I think dot diagonal is from NumPy. Confusion matrix returns
NumPy is also called,
array.
no? Yeah, NumPy is also there.
No, answering a question, sir. Her question was, what is dot diagonal? Which library does it belong to?
You can try this, ma.
Yes, sir.
NP dot.
Sir, I can't use NP dot diagonal, sir. It's showing error, sir.
Just a minute.
Missing that position marking.
Wait, I'll
Yes.
check out. Where is the CM? I'll just check out, okay? It's you can also help me out in seeing the screen. I've imported
CM
pandas.
is right below. CM is right below your import from sklearn.metrics. CM is equal to confusion.
CM is equal to confusion matrix. Okay, so it is not. I have to do it like this only, no? I think if I do this, this is more than enough. It is not NP then.
Yes, sir.
CM.
I think
CM
if I do
CM will be a NumPy array. Confusion matrix return is a NumPy array.
Correct, but I have to. That CM is nothing but the instance returned from confusion matrix.
Correct.
It is an array, but it is written from confusion matrix.
Yes.
Yeah, I think this should solve the error.
Yes, sir.
Okay, shall we move ahead?
Sir,
Yeah.
even in report we got the accuracy, sir. It
I
was
think you get
printing
only.
accuracy.
You are getting it printed, is it?
Yes, sir.
Okay, is the both accuracy the same? In the report and as well as in the calculated one?
Yes, sir.
Showing
For me
one
it
and
was-
one.
It's not. Yeah, it cannot be one. No, it will be completely overfit then.
So for me it was 0.99 and then 0.9927. So yeah, I think it's the same.
Somewhere like that. Okay, so if it is the same, fine. One means probably your the calculator is doing rounding it off.
Yes, sir.
Some of your friends suggested some other methods. You can try with that also. Okay, so this is not for analysis. This is just to understand. This is just to see how to implement it. The main part of the analysis we have to do here. Allow me to put the slides onto your presentation. Just a minute. So we'll try to understand why this this kernel something is there. Okay, we will take it very slowly. We will not rush such that only some people may get the hold of it and the others may not. So there will be one or two slides from today which we will be relooking tomorrow, because that is the actual. Or you can try it yourself. If not, we can relook tomorrow itself. Tomorrow also. Okay. So we will do the whole thing, but then there will be 2 or 3 slides which is not that clear today. Hope both the sections are able to see the screen. Virupakshi and whom did I call again? I forgot. Yeah, both the meetings are seeing the screen properly, right? Yeah. So this is the gist of it. So we are trying to come up with a maximum margin of when compared. It's nothing but like a linear regression, but we want the maximum margin to reduce the number of errors. But you can see in the derivation again will include some amount of errors as well. Okay, let us see how it is done. So any two set of data, we will have many possible classifiers, but which one is the best we have to choose. So it is better if it has a maximum margin. So this already we have done, but I'm just rushing through. So between these two data sets, I can have any line. Okay, any line. There's many lines like this, but I have to see which one is the best. Each line will have some part where the error can be introduced. Okay, instead of that, take the boundary data points, not only those two, like those two. Okay, and have a maximum margin or a wide margin separator, which will push against the marginal data set at the input data points or training data points. Yeah. Why maximum margin? Because I don't want any data set to be there inside that. Okay, so we'll call that line center, the exact center line as wx plus b is equal to 0, where the hyperplane is there. One thing is that if you have a 2D plot, then the hyperplane, 2 dimension, if you have one feature, then it will be 2 dimension, the scatter plot. So your hyperplane will be in d minus 1 thing. If you have 3 features, then it will be a 2D plot. The hyperplane will be 2D. If you have 4 features, then it will be 3D, something like that. Okay, so this W could be anything. W could be W1 x1, W2 x2, W3 x3, whatever it is, plus W0 or B. So effectively W is, in this case, it is W1, W2, and X is X1, X2. It could be more or less also. So we'll take one of the class as +1 and one of the classes as -1. One which is above, if Wx plus B is greater than or equal to 0, we'll take it as +1. If it is lesser than 0, then we will take it as -1. Two classes. What is the distance expression for point X to a line Wx plus B? So what is the distance from that point X to the line T? Effectively, we have to project the W line onto it. Now, how much of W it is there? Hope you are understanding. Can I do it somewhat like this? Okay, this is how it is done. How did we do this? This is how it is done. So we are taking that vector W1, W2 that is perpendicular to the boundaries, obviously the weight vector. So we are choosing X plus is the closest point for one class, X minus is the closest point for the other class. So R is a scalar point value. So you need some R into W, which will be the distance between the margin and the closest to +1 point or closest to -1 point. The closest 2 points in the margin is Wx plus B is equal to -1, Wx plus B is equal to +1. So in Wx minus, X minus is the closest minus point and X plus is the closest plus point. So then you can see the solution, you can do it yourself. So finally you will get 2 by root of WTW. So you're calculating the value of R and then finally replacing it. R into W. Say margin M. Some places it is positive, some capital M, some places it is small m. Well, is this okay?
So in the last slide, what do we achieve by calculating the shortest distance of a point from a line? Which
That will
point
come.
was that?
That is what is done clearly here. In the last slide, it was the distance between say +1 to 0 or the midline or -1 to 0. Here we are doing it the whole margin.
Okay, understood.
Yeah. Okay, this slide is nothing but the detailed explanation for the previous one. Okay. So get the margin 2 by root of W2 by W. Now what is the point here is we have to maximize this margin. If we have to maximize we have to maximize the margin in such a way that it pushes against the two classes. That is the requirement. Okay, we'll see that. So M is equal to 2 by, just a minute, I think 1 minute, give me some time, I have done a lot of changes. Okay, I have to rearrange. Okay, I have to rearrange. Okay, can you see the slides now? Okay, okay. I'll just share. I hope both the meetings can see the slides now. So effectively a point is x, and I have a function phi of x which is acting on it, which is actually the classifier. So the decision boundary is wt phi of x plus b is equal to 0. So b is w naught or bias. So I have to maximize this h or maximize this wt phi of x plus b is equal to 0. Hope you got to know what is the problem, what we have to do. We have seen how to calculate the max. Okay, for a given W and B value, we know how to calculate the maximum margin. But for for a general case, we have to find out how to do that. Okay, so how to measure the distance? Again, we are seeing this again. I hope this is clear. This is pretty simple, no? Ax plus by plus c is equal to 0. So can I write like this? Can anybody tell what is that is written there? Ax naught plus by naught plus c divided by root of a square plus b square.
Distance of the point from the line.
Yeah, that is actually the length of the line. Can I tell that it is the length of the line?
Yeah, the shortest shortest distance from the line. Yeah.
The dashed line. And can anybody tell me what is this d of phi of x naught is equal to?
Matrix measure of the same thing.
The same thing in two forms.
Yeah. It's the more generalized form.
Yeah. Anybody having doubts here? You should have told me, no? From long time, is it? Okay. Sorry. Yeah, understood. Yeah, so I understood now. So this ax naught plus by naught plus c by root of a square plus b square is nothing but the distance between x naught y naught to that line a. Okay, the diagonal line. And d of phi of x naught is the same thing written in the general form. Okay, yeah, I'll repeat. I understood. Sorry. Okay, so to just visualize this, if you take a example, say x is equal to -3, y is equal to -1, and as you can read, x is equal to -1, y is equal to -1, the blue dots, x is equal to 2 and y is equal to 1, the red dot, you can have many separators there. As shown, not only three is shown on the slide, I think you can have more than 3 also, more number of separators which can separate the blue dots and the red dots. Okay, so if I just follow the mouse here, so we can write the margin constraints like this. So one margin would be -3a plus b lesser than 1, and which tells me that b should be lesser than 3a minus 1. Okay, so for the first point, the second point I can put it like this, and the third point I can put it like this. So I'm putting constraints as per each point. Now I can do it easily because I have only some number of points here. Okay, so one line is plotted according to this. This is because I think with the blue point. This is also with one more blue point, and this is with the red point, as shown in the previous. That was shown in the previous slide. I'll just go back and come to the slide again. So there are 2 blue and 1 red. So according to that, we have written the constraints. So what is the constraints here? Margin constraints. B has to be lesser than 3a minus 1, B has to be lesser than a minus 1, B has to be greater than minus 2a plus 1. That means, are you convinced that this green shaded area is the one where the separator has to lie?
Yes.
Yeah, the other meeting? Okay. Fine. So now roughly if I take now here in these 3 margins, the constraints, I need to come up with a value of A which satisfies all the 3. That is nothing but the green condition, a green area. So if I take A is equal to 1, okay, and if I put it back, okay, then if I minimize, then I'll get 0.6, A is equal to 0.66 and B is equal to minus 0.33. Okay, that would be somewhere here. Okay, roughly I can come up with the point which is there in the green area. That point could be here, or it could have been here, or it could have been here, or it could have been here. Hope you can see the circles which I'm drawing on the slide. So it could have been anywhere in this green area. Okay, one example is this one. One example is this black dot which is printed in this line. The other examples could be anything. But which is the best thing? Which is the best place where the A value would be for fulfilling all the constraints? That would be the optimal, tightest thing. That would be here. So this is nothing but minimizing the A, or basically maximizing the margin. So all our linear classifiers were somewhere here. Okay, are they the best one? According to the tool we had, we got the best fit there. Okay, but if I increase the margin, I can come up to this optimal thing, the tight fit. Hope you people got a rough idea about it. Okay,
So
going
this
there.
will optimize both A and B, right? Not just
Yeah, A and B, not only A and B. Here in the example, we have taken the value of A is equal to 1, B is equal to 0. Okay, we'll get 1 point. If I take A is equal to something, B is equal to something, I get 1 more point. First of all, I have to take the values of A and B in such a way that I'm in this green area only. If I take any point in this non-green area, then it is no point, right? I'm missing one or the other constraints. These points are not required for me because I'm missing the constraint. So I have to take A and B values in such a way that the points which I'm considering A and B value should be in this green area only. What do you mean by A and B value being this green area? The line being able to separate this red and blue dots. Okay. Now the point is, which is the best line which separates it? Okay, that would be the value of A and B in such a way that it is the value of A and B is the line in such a way that the value of A and B is somewhere here, which is just fitting all the three constraints. It is not doing much. It is not missing any constraint. Okay, is that fine? Both the meetings? Yeah. Go ahead. Yeah. We follow a tool. We let us assume that we are following a tool to minimize A. So I'm minimizing A to such a small value that it will just fit the constraints. What are the constraints? The three constraints shown in the slide. Accordingly, I'll find the B value. So effectively, the minimum value of A which fits the constraints is getting me a B value of this much. Okay, is that fine, everybody? Okay, fine. So effectively, we have to do that. So in the previous slide, if I show you, so we have many points here. So effectively, we have to write lines for each and every point, put constraints of each and every point, and then find out a value which fits all the points. But this is a tedious process to be done every time, because as the number of data set increases, it is highly impossible for us to do it. So rather than that, okay. Yeah, so we have to be effectively minimizing this. So how to minimize it without doing it for every point? Let us see that. Okay, so again I'm telling, so I want to find out the minimum value of that particular distance, the minimum distance so the minimum margin. Okay, hope the slide is, all the green thing is greater than 0, all the red things are lesser than 0, so class 1 and class 0. So weight matrix is nothing but the minimum of the distance. See, I am trying to minimize those points A and B in such a way. So if I'm minimizing this point A and B, I'm not going to get a line like this. I'm going to get a hyperplane. So I have to maximize the margin. Okay, I have to do like this, somewhat like this. Okay, so we'll go ahead. So the left part of the slide is the same, the previous one. So when I'm predicting using this line or hyperplane defined by W transpose phi of x plus b, y of that much. If it is greater than or equal to 0, then it is correct class. If it is lesser than 0, then it is an incorrect class. Yeah. So this we know, no? We can do it, right? In the previous slide, we have seen this, no? From here to here. So effectively, if I have the minimum possible value for this predict the WT phi of xn plus b divided by norm of w, then I'll get a perfect solution. But this perfect separation. But this solution would be only for linear cases, linearly separable cases. It would not be for linearly unseparable cases. Okay, keep that in mind. This is where kernel comes into picture. So this should be only for linearly separable cases. Okay, I will go ahead. So effectively we have to do this from the previous slide. So to avoid confusion, let us call this whole term as 1. The one which I am rounding it off.
So I don't understand what yn of the
that is the predicted value. That is the output.
Also, because the previous statement was omega star is equal to argument max minimum of that distance.
Yeah, that omega star is nothing but my that omega star is nothing but my perfect weight for thing, right?
Correct. Yeah, but from there we've got next step we've gotten a yn. How do we get that extra one?
See, that y is nothing but the class predictor.
Okay.
Okay, that is nothing but the class, the output.
Okay, but how did we change that from like the previous step to this step? I understood that yn is the output that gives the class passes the class, but how do we go from the previous step to this step? How do we get that yn over there?
See, if I want a perfect separation, then I need this yn of wt phi of x1 plus b to be either 0 or greater than 0 or equal to 0 or lesser than 0.
Okay.
Okay, so effectively
the left hand side will not be omega star, right? It will be something else.
Where in the equation
left hand side of the equation that you've circled in black.
Okay. That won't be
something else.
Be here, that's all.
Yeah.
Effectively, your yn is nothing but the distance between that point to thing, no? Depending on which, if that distance is greater than 0, you will tell that it is +1. If the distance is lesser than 0, Yeah, so your yn is not actually +1 and -1. Like in logistic regression, if you remember, we get some value. We consider it to be as +1 or -1 depending on that threshold.
The threshold is margin by 2.
Yeah, threshold is margin by 2. Okay, that is how we put that y inside. Okay, so we'll call this as 1. So we'll take a constant that is multiplied, C, for all the weights. So we'll take this constant. So what this allows is, this allows something called as scaling, which we can see with some examples. So effectively, I want this to be done. Now 1 is nothing but the form of SVM. This is what we are going to solve. We are supposed to solve. So in most of the videos or books or whatever you see, they'll tell primal form. They'll come up to primal form and then they'll tell, if you solve this, you get something. So that something will be the next equation. So in between there is some amount of mathematical work that has to be done from primal form to. Okay, what next? How are we doing on time?
we pass time, sir. We have 3 minutes for the next class.
Okay. Then I'll do one thing. Primal form, I'll leave it here only. I'll put this onto the drive. The whole derivation is also there. So I'll put this onto the drive. You go through until primal form. Any doubts we can discuss until this slide, primal form. Then we can continue how to go on doing the same with the nonlinear as well, and then adding slacks, etc., and all. Okay, so we've done until primal form. We have formulated what we have to do with respect to primal form. I think you have very less time to log into the next class. So we will stop it here. Would that be fine? Yeah. Just a minute. I'll give you the QR code for the attendance. Just a minute. You can mark. I think it is on the screen for one section, one meeting. I'll put it on screen for the second one as well. Thanks to the student who suggested I could do it with 2 meetings. Otherwise, with that only we ate up 15 minutes of the class. Hope all of you are able to see the QR code.
No, sir. Sir, it says the form is no longer accepting responses.
Just a minute. I'll enable it.
Sir, could you share the QR code once again?
Yeah. I got it.
Thank you, sir.
Sir, it's written that attendance is for B and D sections.
That's fine. The title, I was not sure about taking all the 4 sections today. That's fine. Okay.
Yes, sir.
Yeah. Hope it should accept the responses now. And I'll change it to A, B, C, and D. The date is fine. Yeah. I have one. Both the meetings can see the QR code, right?
Sir, section option has only B and D.
I'll change that. This is done for, I think now it should come for A and C section.
Yes, sir.
Yeah. You can mark the attendance and leave the meeting and log into the next class. Yeah. Thank you all. Tomorrow we'll start off from wherever we left.
Hello, sir.
Yeah, Ankit. Why you are opening from non-RVC ID? I think so. When everybody can know, please see you would have done some mistake. I think it is non-RVC. Okay, I've got 100 responses already.
No, same not able to open the forms.
Yeah, RVC ID ಇಲ್ದೇ ಇರಬೇಕು. 104 ರೆಸ್ಪಾನ್ಸ್ ಆಯ್ತಲ್ವಾ? So there is some access mistake from your end.
So can you share the form link in the chat?
Sure. I'll do it in a minute. Less than a minute. Both the chat meetings chat window I'll put.
Ma'am, recording.
Huh. Yeah. So I hope you remember what we discussed in last class. Like we had a pseudo NMOS logic where PMOS was connected as a load. So why it is pseudo NMOS? That means the output or input will be output will be decided by NMOS pull down network alone. So it should be only NMOS. If it's pseudo PMOS, then you will have only P networks like similar to the as that of CMOS structure, and in the N network you have only single NMOS. Okay, then it's a pseudo PMOS. So what we have for you is pseudo NMOS. See, we can try this structure with the different types of loads, like depletion type of load or dedicated NMOS load. So, but still, this logic pseudo NMOS with a P type of load, like it is easy for us to, play with the sizing. If it is a type of device, the current conduction in a given a same input, the current conduction in a PMOS is much lesser than the current conduction in the NMOS. Okay, when input and all conditions are same, like you have equal width, you have equal length, you have threshold voltage of N is equal to magnitude of threshold voltage of P. If all other conditions, those conditions are met, so current conduction is P is much lesser than the current conduction in N. So P is more resistive compared to N. So it is easy for us to play with widths, currents, and all when we take PMOS. That's why the ideal load is a PMOS for a pseudo NMOS structure. Okay, it doesn't mean that you have to use always PMOS as a load. You can try with other types of load as well, but this is the best one. Okay, and from the previous class we tried to derive like the relation, like the sizing. So why we have to do sizing? So what is a takeover from the previous discussion is like no point of time, like say imagine input is VDD. If input is equal to VDD, then both the devices are on. So what is the effective Vout voltage? It's a non-zero value. That voltage I called as VOL. I wanted to somehow make this VOL close to zero. So to derive that, like I want to know like on what factor VOL is purely dependent on. So from these discussion, like from the previous class, what we have is like the inference is like VOL is perfectly, purely dependent on what is the ratio between P width and N width, N mass width and the P mass width, correct? So I think the derivation you remember, right? So when input is VDD, then NMOS is operating in the linear region, PMOS is operating in saturation region. When you equate two currents, say A and NMOS, say V out value is VOL, right? So NMOS VDS is nothing but VOL, and similarly PMOS VDS also you can calculate, but in this case I have simply taken as VDS saturation. So this way if I derive, I can get to know that like VOL is purely dependent on the ratio between the widths of PMOS and the NMOS. Okay, this was the idea. Like the plot was given, what it says, like say if I fix NMOS width equal to WN equal to 16, and if P width, P is what? So this value is P. If I take it as 4, so WP is 4, WN is 16, so the ratio is going to be VOL is dependent on WP by WN, so it is like 4 by 16, so it is about like 1/4. That means you have to size the PMOS 1/4 of that of NMOS. It's not like you have to take it 16, you take any other width, but the ratio if you make around like 1/4, then what you can see is like the VOL is almost close to 0. So if you increase the width of PMOS. So the second case, P is taken as 14 by 16. So little higher value, then the VOL is again close to 0 but little high. Okay. So similarly, if you take another width, 24 bar 16 by 16, that means PMOS is width is much higher than the NMOS width. Then what happens? VOL is a completely non-zero value, and it is a little high value. So what happens is like the load device may detect this value as a logic 1 or intermediate state. So there will be some false logic recognition. Instead of logic 0, it will be recognized as intermediate state or something, or logic 1, depends on what is the VDD value of that particular technology. Okay. So that is a problem. So it is always best to make it WP by WL little less. So how much? WP much lesser than the WN. So typically full load value is like we try to make it like WP 1/4 of that of WN, but it's a range. Okay, you can even try with say around like 1/3 to 1/6. That's fine, no problem. That means you are making a PMOS. If I say 1/4, that means you are making PMOS 4 times weaker than NMOS. Okay. If it is 1/3, then it is like you are making PMOS 3 times weaker than the NMOS. Here, the other case, 6 times weaker than the NMOS. Okay. It doesn't mean that you have to take this as a width. It is like the ratio between the width should be 1/4 or 1/3 or 1/5 or 1/6. It's anything ranging from 1/3 to 1/6. They find it like it is the best way to use. Like there should be some proof for that, like why they feel it is the best. Okay, the ratio in this particular range. So let me give you an example. I have a particular say pseudo NMOS NOT gate, and it works on the some say 0.25 micrometer technology or 250 nanometer technology. This one simple reference, okay, which I took. So VDD value is around 2 volt, okay, not 2.5. Around 2 volt is the VDD value. Can you all hear me? You're there, right?
Yes, ma'am.
Okay. Yes. Why the strength is less today in class? Do you have any other work?
Ma'am, it's more than usual. It's 47 today.
What 47? I'm seeing only 26. Okay. Oh, updated now. Sorry. Okay. More than usual. Definitely.
Yeah.
Okay. Anyways, so let me take VDD value around 2 volt. This reference I took for 0.25 micrometer technology, okay, or 250 nanometer technology. The reference voltage range is around 2 volt. Okay, so let me take
just an example.
Just an example, okay. No, I mean randomly I took. So this I took from some reference, not from your textbook data or something. From I refer to some paper. From that I got to know that I think I can go with this. This is around 2 volt. Sorry, not volt. This is around.
What are those micrometer? What is the length range? Is that W or is that L?
No,
the range that you put in the bracket.
No. It's a technology. Okay, technology. Okay. So it's almost close to L. Okay. Technology. You have 180 nanometer technology, 45 nanometer technology. Correct?
So you're giving the range for which these tools.
Yes. See what happens, when the technology, when you're changing, say 250 to 180 to 45, I think I've told you, like we will be scaling by a value of lambda equal to √2 every time. Okay. So when we scale, what will happen? No, it's not enough if we scale only the length. We'll immediately start scaling voltage levels also.
Yeah.
Okay. So that's the thing. Okay. This is some basic data I have. So now the case is like W by L of N is equal to 2. So as I said, it's a one particular technology. L value is fixed. I cannot change. Rather, I can simply take it as Wn because L is same, right? Wn is approximately 2 because it's when you compare this with the WP, because for WP, PMOS, for PMOS also L will remain the same. So I think it has got no meaning now. It's simply WP to WL ratio. Okay. So WN is approximately 2. And what I'll do is like, let me calculate the value of VOL. So I have already given you the equation how to calculate VOL for various values of WP. Let me take it for 4 first case. So if I have 4, then for this particular technology that it is resulting the VOL value, it is equal to 0.69 volt. See, you imagine it's around, VDD is around 2 volt and this is 0.69 volt. I mean, it is a little high. Okay, it will be definitely higher than the threshold voltage of NMOS. That's because, say if you imagine 5 volt as a VDD, we still take threshold voltage around 0.6 to 0.7. So it will be definitely high. So this is going to affect the noise margin of driver connected. So if I change the width of P, so what will happen? WP, the first case, WP to WN ratio is like 4/2. Okay, so PMOS is stronger than NMOS now. Okay, so now second case, what I'm doing is like I'm taking PMOS width as 2, okay, ratio as 2. So what will happen when I'm decreasing the size of PMOS? So what is seen now? See, this particular voltage is suddenly dropped to 0.27 VOL. So if I take another condition, I'll try to decrease it further. Okay, I'm decreasing it to 1. Then what is seen? Around this much. Okay, this is some simulation they did. From that I took the values. Okay, then once again they dropped it to around 0.5. So it is like WP to WN ratio is 0.5 divided by 2. Okay, the third case is 1 divided by 2, that's 0.5. Okay, fourth case is 0.5 divided by 2, like that.
Is this a practical result or a theoretical result?
It's a practical result. From simulation they found out this one.
Theoretically it's not correct.
Yeah, so it's a practical result. They found it from the simulation. Okay, that values I took. So for around 0.25 value, it was around, see, like as you go on, see why I am writing all these is like, you can see as you go on reducing the width of the PMOS, what happens? The VOL is also starts reducing. So it has got a direct relation. So now they are using the non-zero VOL close to 0 is just by reducing the width of PMOS, or rather I can say just by reducing the WP to WN ratio. Okay, so no matter whatever is the width of WP or WN, I have to maintain certain ratio. So when I look at this, like I think 0.2 and below somewhere here. Okay, so if I look at this, the ratio is WP is 1, WN is anyways fixed value, so I get around 0.5. Okay, anything below that, this was the range. Why they have decided like the ratio should be around 1/3 to 1/6. That's because when the simulation, you can see when the ratio becomes that, the VOL value starts dropping. So we can still take it as logic level 0 because it's dropping below the threshold voltage. Got the point? So it is not going to change the noise margin of load connected. Is it clear, student?
Now, was it threshold voltage in the case of this?
It will be around it will be definitely around 0.2 to 0.3 because VDD itself is around 2 volt.
Okay. By a voltage being defined as a level 0.
No. Logic.
Or are you talking about VT?
VT.
Okay. Yeah.
See, when you
noise margin, it will be the same thing only. Yeah.
Noise margin will be decided based on VT value, right?
Correct.
It's basic reference.
Ma'am, these values are on which technology? Is it 250 nano?
250 nanometer. See, this was not your textbook data or something. Okay, I referred to some material. In the sense, some simulation they did. Like what happens to this? I mean, implication of ratio on the plot. Okay, so they took around 250 nanometer technology.
And for VDD 2 volt, so 2 factors.
2 volt, yeah.
Okay.
See, it is like if you are taking around 1, it's like they took 2 volt, it can go up to 2.5 volt. Okay, they took for the simulation approximately 2 volts they have taken. So if it is 180 nanometer technology, so VDD value reference is around 1.8 volt. Okay, as technology is scaled, we even scale the VDD values. So when I say VDD is 1.8, so threshold voltage is again less. It will be around 0.3, yeah, or 0.2, like that.
Yes, ma'am.
Yeah.
Can you share this document or resource?
Yeah, definitely.
When you find time.
Yeah, sure. So now this was the idea, it should be like PMOS should be like at least 1/3 or 1/4 of that of NMOS, so that you will have almost close VOL level. So for hereafter, for our discussion, what we'll take is like we'll take the PMOS size is 1/4 of, because in the textbook reference they have taken it for 1/4, but it doesn't mean that you have to take that. They've even given this also 1/3 to 1/6, but every example they have scaled with respect to this ratio 1/4. So that means what? The PMOS should be 4 times weaker than the NMOS, so that VOL is almost close to 0. Okay. So that's our basic idea. Like now the question is like we are very much interested in CMOS technology, right? So when I say CMOS technology, so for me the basics CMOS inverter, the sizing of a basic CMOS inverter is well known now. So unit size inverter. So let me try to keep this also in mind, so that when I'm sizing, I'll try to see that can I match the sizing with respect to the CMOS inverter as well. So let us see that whether it is possible or not. So now what I have here now is a PMOS which is permanently connected to ground. When input is 0, I don't have any issue because there is no static power dissipation because NMOS is off. But whenever the input is VDD, then I have some issue with the static power dissipation as well as the value of VOL. Okay. So now the idea is I have to size it. So now how do I size it? So while sizing, to match the delay, we try to size every CMOS logic with respect to unit sized inverter. So let us try to match it with this also. Okay. So now the case is like, say you have a capacitor. So one path is charging, another path is discharging.
What is that table about?
Table. Hey, I'll come to that. Don't worry. Okay.
Okay.
Look at this now. Okay, one path is charging, another path is discharging. So it is charged by some amount, discharged by some amount. So I have to decide on the size now. So directly how to decide? It's very hard to decide. So let us first analyze how much current it is taking while charging and discharging. So at output node, say if I believe that at output node, say I is the current I want, because why I take this I as a reference, that's because in a CMOS inverter the output current is I. Okay, it is charged by I and it discharges the same current. Okay, charging and discharging. But now if I want to match to that same I as that of CMOS inverter, now the challenge is I'm trying to scale it. I want to make, because it's a demand from pseudo NMOS logic that I have to reduce the size of PMOS, but wherein in a CMOS, to match to that I have to increase the size of PMOS. So it is like exactly opposite. Now how do I find out? It's like, say, now in a CMOS pseudo NMOS logic, since the output is decided only by the NMOS, it's a pseudo NMOS, so the logic is decided based on NMOS. Let us decide everything with respect to NMOS. Let us ignore the load, okay, for time being, because if I start deciding everything with respect to load, then whether it is a CMOS inverter or a NAND gate or a NOR gate, for everything sizing will become equal. That's because Whether it's a NOT gate, NAND gate, NOR gate, you will be at the load, you will be having single device. Okay, let us not do that. The logic will be decided by NMOS structure. So we have to decide the sizing or the current value, I mean proper sizing for required current value based on NMOS, not based on PMOS. Okay, so how we are going to do that? See, I need some, say, I current to be flown while charging or discharging. Now, if it is a CMOS, regular CMOS inverter, then I would say while charging and while discharging. So now I want I current to be flown while discharging, because now for me what is important is NMOS. So NMOS is in the discharge path. So let me look at the current which I need while discharging. So this current I has to be equated to the charging and discharging current of CMOS inverter. Okay, so this has to be matched. So I need I current. So now let me believe that I have size. I mean, I have to size this pseudo NMOS such that PMOS is 1/4 of that of NMOS. That means you have to size. I mean, PMOS 4 times weaker than the NMOS. Okay, so that means what? While discharging, it's like there are two paths you can see. While discharging means I am not just looking at the NMOS. NMOS is discharging. Meantime, PMOS is trying to charge, right? So this will be always on, right? So, but this PMOS is on a weaker side. So let me write. So if NMOS is discharging some 4 units of current, 4 into some units of current, okay? 4 times stronger, right? NMOS 4 times stronger. X I am representing for some current, okay? So it is conducting some 4x times of current, but I mean discharging, but now NMOS is charging by 1 unit of current. This is what is the meaning. So effective current, when you look at it, is like difference between this discharge current and the charge current. So that means NMOS is trying to discharge 4 units of current while PMOS is trying to charge 1 unit of current. So effective current what I get is like 4x minus 1x. So what is that 1 unit of current? Let us find out. What is that x value? X value will be around I by 3. That means what? PMOS
passes on that I by 3.
PMOS conducting how much current? I by 3.
I by 3.
Conducting I by 3 current. NMOS conducting how much? 4I by 3. Yes, it is 4 times of x, right? Got the point? So if you want to get effective current I, and if you make sure that the size of PMOS is 1/4 of that of NMOS, then the current conduction in a PMOS is just I by 3, and current conduction in NMOS is going to be 4I by 3. So that you will have effective current, because it's like there are two paths now. There is a charging path and a discharging path. So effective current I, what I can say is, I can measure I when this is the condition. Okay, this particular current I is equated to the current which is produced by regular CMOS inverter. Okay, so if I want to get that much of current, then PMOS should conduct I by 3 current and NMOS should conduct 4I by 3 current. Okay, if I want
I is the rate of discharge of the capacitor, right?
Yeah, it's a relative. Yeah, we can say that. Yes, correct.
Okay.
I is the discharge current. Yeah. So that means if I want to make I as a discharge current, NMOS should pull 4I by 3 amount of current, while PMOS is charging I by 3 amount of current. Got the point? Yes. Do you have any doubts?
Ma'am, is this I proportional to the current in the normal CMOS, and then we are like trying to bring the proportion between CMOS and the pseudo CMOS.
That's what we are doing now.
Okay, so both the I's are just proportional.
Same. It's both are same. That's why I'm written here. No, the same I. Okay. This I and this I both should be same. Okay.
Ma'am, can you repeat that, ma'am? Are we trying to? In the beginning you said that we're trying to size the pseudo NMOS based on NMOS. Like now I'm confused. Like, are we trying to design the pseudo NMOS based on the discharge current that we see in CMOS?
Yeah. Yes. Yes.
Okay, but why are we doing that again? I'm sorry, I don't.
See, one thing is like in in a CMOS, one best part is like, say, when you compare to the CMOS inverter, it has got equal charging and discharge part. That's the best thing. So it's like why I'm migrating to pseudo NMOS when I have a beautiful logic like CMOS. It's
Sizing.
only the area coverage, okay?
Yeah.
But when I want to design pseudo NMOS, I have to improve the area only. I should not kill its quality, right?
Correct.
Like I have to maintain that originality. That's why I want to still represent current size, everything with respect to CMOS inverter. So I want to prove that, see, entire load I'm replacing by one single PMOS transistor and see
So
the
getting the
effect
same
is same.
result.
Yeah, I want to do that. Got the point?
Okay, but here we're only checking with respect to discharge, right? Charging
Yeah,
will not be the
charging.
same then.
See, what happens is like, so charging and discharge, how much it should charge or discharge, that becomes, that is decided based on this, how much ratio I am taking. Ultimately, whatever is the ratio, I want I current. Okay.
I is the rate of discharge of the capacitor when I'm pulling the logic low.
Low.
Correct?
Yes.
Yeah.
Y
So
to 0.
we're essentially sizing for that case only.
Only. That's
yeah.
why I'm considering, because discharge, I should consider what path NMOS section only. Correct?
Yes, ma'am. So my doubt is, it won't be the exact same as the CMOS logic because we're not considering the charging state. That is when the device goes from 0 to 1.
Yeah, see, there will
In
be
that case, it will
definitely,
not be the same as CMOS.
it won't be same. Pull down, I am trying to change, keep
it
same
the
as that of CMOS inverter. Pull up I can't because it's one single fixed load. Okay.
Exactly.
Okay. So if you look at the charging time and the discharging time, it will be different. Because whether you take, say, CMOS, pseudo NMOS not, pseudo NMOS, for example, if you take pseudo NMOS
capacitance will vary. Capacitance will vary.
Yeah, this will vary, and meantime, see, the load will be like some one fixed load, right? Always.
Yes, ma'am.
Okay. Yeah. So I want to do with respect to the discharge only, so that I can do only with the pull down. And see, output logic will be decided by the V in. V in is now connected to NMOS logics only, NMOS devices only. So I have to, whatever I do or sizing or current analysis I do, I'll do with respect to NMOS devices, because this pull down rate is more important for me now with respect to pseudo NMOS. Okay.
Ma'am, what about the resistances in this?
So that will change now. Like, see, now let us come to that sizing, then we'll analyze what happens. It will change, okay? Same as that of CMOS inverter, but what I'm trying to keep same is the current. Okay?
So we'll be doing the sizing and discussing the resistors.
Yes. I will not specifically have any discussion on resistors here. We just do the sizing accordingly, okay? So let us do that now first. Okay, so now one thing is clear, right? Like if I want to make PMOS like 4 times weaker than NMOS, if I'm making that, it's understood that PMOS is conducting I/3 of current and NMOS is conducting 4I/3 of current, so that I can maintain discharge rate with respect to I. Okay, so that's the thing. So now if I want to make, say now it has to conduct. So what is the condition now? PMOS should conduct I/3 of current. So let me shift to this part now. Okay. So if I'm at the CMOS now, if I current to be conducted by PMOS, what should be the size of PMOS in CMOS technology? And given that PMOS size is what? Yes? Yes or no?
2 times.
2 times.
3.
Okay.
Yeah.
2 times, because CMOS inverter, if I want to make sure that I current is conducted, then PMOS size is double that of NMOS, correct, right? So PMOS size is 2. So now the question is, I want to make, with respect to, see, I'm same thing, I'm shifting to now pseudo NMOS, okay? If I want to make I/3 current to be flown in the PMOS, what should be the size? I current, then 2 is the size. I/3, then what should be the size? 2 divided by 3. So 2 by 3 is the size of, PMOS. Got the point?
2 by 3 of the NMOS in the CMOS inverter, right?
Inverter, yes.
Okay.
Yeah. So now
Ma'am, 2 by 3, you're talking about current here, right?
Current. See, wait. Let me once again explain. See, I try to maintain I of CMOS equal to I of pseudo NMOS, correct? Yes?
Yes,
Yeah.
ma'am.
So if I want this device to conduct I current, what should be the size of PMOS? Unit size CMOS inverter, 2 is the size of PMOS. Correct? WP should be 2. Yes, Lalit?
Yes, ma'am.
Okay. So now how much current it should conduct? If you shift to NMOS device, it should conduct only I/3, not I. If it would have been I current, then I should have sized it to 2 only. Now it is like I/3 it has to conduct. So what should be the size? If I want I current to be conducted, then 2 is the size. Now I/3 I have to make sure that it should conduct. Then size should be 2/3. Got the point? To conduct I current, it needs 2 units. That's fine. Okay, I current. So now I/3 current it should conduct. So the size should be 2/3. Okay. So now to discharge I current, NMOS size is 1. But now, like, it should discharge how much current? 4 I/3 current should be discharged. What should be the size of NMOS? Can you tell me?
8/3.
What 8/3? NMOS? 4/3.
Ma'am, maybe 4/3.
Ma'am,
Maybe
the size
4
ratio
by 3
should
only.
be.
Huh?
Ma'am, shouldn't the size be 1/4, ma'am? Ratio 1/4. That would be 1/2. If you have 2/3 and 4/3.
Oh my God. See, if I want I current, the size should be 1. Now how much current I want? 4 I/3 current I want. So what should be the size? 4/3.
4/3, but the ratio of the PMOS and NMOS should be 1/4, right?
No, this is not the ratio, man. This is not the ratio. See, one thing, like, you don't take directly like, oh, now what is it, 2/3 divided by 4/3, all these circus, you please take it out. See, now it's not just about the ratio, okay? When I say I want the PMOS 1/4 the strength of NMOS, what does it mean? It should conduct 1/4 the current of that of NMOS kind. I mean, it should be weaker, 1/4 weaker. It is not like, see, but I while doing that, I have to maintain the currents equal. Okay. So now in the PMOS, regular CMOS, what was the point was, like, whenever PMOS was on, NMOS was off. Okay, but here that is not the case. Whenever NMOS is on, PMOS is also on. Got the point? So you cannot just size it as in the CMOS, because you get the case where V in is VDD, both the devices are on. One path is charging, another path is discharging. If I want to make, see why we have derived that VOL expression, it is like the ratio is WP by WL, WN. The VOL dependent on that. That means if you make PMOS weaker than NMOS, VOL is a minimum value. That's the indication. Like, so now I can directly make, like, I can keep PMOS size 4 and NMOS size 16. So what will happen, as seen in the graph, it is almost minimum. We can do that. But now the idea is, like, it's not only enough, it's not just enough. Okay, I have to even make sure that the current conduction any CMOS NOT gate, which was I, that same I want to maintain. Okay, so if I want to maintain I, along with the condition that I have to reduce the size of PMOS compared to NMOS, then how I'm going to do, that's what we did. What the point now? If it was one agenda of like just reducing the size and where the current I need not to bother, then it would have been only WP by WN. So then it was 4 in the P and 16 in N. Okay, finished. But now the agenda here is like, that's not just enough. I want to compare that, pseudo NMOS NOT gate with the CMOS NOT gate. When I want to compare with respect to, say, charging or discharging, so I have to make sure that I, especially the discharging, okay, I have to make sure that same I. So now there are two conditions, not just WP by WN ratio. So it's WP by WN ratio along with the constant I value. Okay, that's why you can't see that when you just take it may not come equal, but when you simulate, you will get it. Yeah. Any other doubt? Is this clear? Are you there, students?
Yes, ma'am.
Yes.
It's clear.
Junaid,
Yes, ma'am.
Junaid, any
Yes,
doubt?
ma'am. No, ma'am, no, ma'am.
No doubt, right? So now
Yeah,
tell me.
because of the one more, like I got my answer. Because of the mobility also there is variation. So
Yeah,
the ratio will
obviously.
come. Yeah, yes, ma'am. Because the mobility is half, right? So from there we'll
Okay.
get value.
Okay, so
Yeah.
now the sizing now, so pull down size, so inverter, right? Pull down size, effective size is 4 by 3, pull up effective size is 2 by 3. Say now if I have, say for example, I have a pseudo NMOS NOR gate. Okay, can you size it according to pseudo NMOS NOT gate? Got the point? What's the question? We have pseudo NMOS NOR gate. Can you size it according to pseudo NMOS NOT gate? Students, please try.
We made a pseudo NMOS NOT gate only, right?
Yeah, pseudo NMOS NOT gate. So now here after this pseudo NMOS NOT gate, I'm starting here, okay, will become a reference.
You use this as a reference.
NOT gate, I have already taken current reference. That's it. The job of CMOS inverter is done. It's over now. So hereafter, for any other pseudo NMOS logic, so this pseudo NMOS NOT gate will become a reference. Got the point? So now can you please try. Now I want you to try pseudo NMOS NOR gate, then 2 input, okay? Pseudo NMOS NAND also you try. One series structure you'll get, another parallel structure. Can you try this and do the sizing quickly? I'm writing NAND gate, okay, because you will have series structure here. So I want to say, Harshita, you had asked me the resistance stuff, right?
Yes, ma'am.
So I want to maintain in this ratio only.
Ma'am, it will become. Can I answer now?
Yeah, see, if it would have been a CMOS, 2 devices in a series, resistance, the sizing will be 2, 2, right? Correct? If it's a regular CMOS. So now if it's a pseudo NMOS, now sizing is 4 by 3. Now I have 2 devices in series. So tell me, what is the sizing?
8 by 3 and 8 by 3, ma'am.
Yes, correct.
8 by 3, 8 by 3.
And pull up?
Pull up you can retain the same.
Yeah, correct. This is correct. Any doubt in sizing? Any one of you? It is still, it will be same as, regular sizing only, but now the reference is different. Here it was a CMOS inverter, reference was 1 unit, now it is 4/3. So you have to size according to 4/3. That's it, in the pull down. Okay. So if it is a NOR gate, any change?
A and B 4/3.
Correct. So this is 2/3 VDD Y. So parallel structure. So you have A, B. So parallel. I mean discharge can happen either through A or through B. So 4/3, 4/3. What is sizing? I hope this is clear now. Another exercise I'm going to give you. Now what we did is like NOT gate, we sized with respect to 1/4 strength. Okay. That means PMOS is 4 times weaker than NMOS. Now I want a pseudo NMOS NOT gate with the 1/3 the strength. That means 1/3 of the strength. So how much weaker I want to make?
3 times weaker. PMOS 3 times weaker.
PMOS 3 times weak. Okay. So now can you tell me what is going to be the size? So you have to start with that some x expression I gave, no? I equal to 4x minus 1x. So with respect to this, you have to derive now and tell me what is going to be the size of
Is it 1 and 2?
1 and 2. One and 2. What do you get? The sizing? Are you there?
In the NOT you will get 1 and 3, ma'am.
1 and 3.
The
So
NOT, you get
others,
1 and
you are
3.
able to do the sizing. Please tell me if you are. So you have to still go with the same. Okay. So it is like if I want to make PMOS, NMOS is 3 times stronger than PMOS. Correct. So it is 3x minus 1x. So x value is going to be I/2. Okay. So I/2 current to be conducted, then PMOS size is going to be 2I/2. So unit is 1. Okay, PMOS. The second part is like 3I/2. Okay. So what is the size?
Ma'am, I didn't understand. Could you repeat again?
See, now what is the question? See, this particular sum we have solved for the strength 1/4, correct? Yeah?
Yes,
so
ma'am.
you want to make it now 1/3.
I'm sorry, ma'am. It should be 3/2. I'm sorry. You can call me. I'm sorry. It
Yeah.
should be 3/2, ma'am. Sorry.
Yeah, that's what. So 1/3. So how to make? You have to get back to the same type of expression now. So if I want to make it 1/3, then total I is going to be 3x minus 1x. Yes? Who asked that question? Who asked me to repeat?
Lalit.
I asked.
Lalit. Lalit.
Yes,
You
ma'am.
got, then it will be 3x minus 1x. Correct? Lalit, x value. What is the x value? I/2. 1 unit of current, that means, x value, so I/2. So that means PMOS should conduct 2 current. What should be the sizing with respect to CMOS inverter? I current, then 2 is the size. I/2 current, then, so PMOS size is 1. Clear?
Yes, ma'am.
Yeah. So now, guys, now I want it to conduct 3 by, what is the current? 3 by 2 current I need to conduct. What is the NMOS current? 3 by 2.
So size is 3 by 2.
3 by 2. So please solve it, no?
Yes,
How about others? None of you asked this question. Junaid, any doubt?
No, ma'am, no, ma'am. You
No.
could do like PMOS as 2 and NMOS 3, then from there you can continue.
Anyways, however you understand. So it is 2 by 3, no, Harsh? 2 by 3. Sorry. 3 by 2.
3 by 2. 3 by 2. CMOS is 1.
Yeah. So this is the case when you have this strength. So for exam, you can get any, okay? So it's not like I taught you only 1 by 4. So it doesn't mean that you will get only that question. You can get it for any value. So you should be able to do sizing. So when I say 1/4, 1/3 is the strength. And if I ask you to design a NOR gate, or a NAND gate, for example, okay, NAND gate, then NAND gate inside you have to size according to 3 by 2 ratio. Got the point? Yes, students?
Yes, ma'am.
Yes. Okay. So now what I have now. Okay. So now the case is like the logical effect. Will there be any effect on that? Because now, you know, as per your previous knowledge on logical effort, like you had some fixed value, like you size the devices with respect to PMOS, CMOS inverter. Then you had logical effort, all calculations. Okay, so now how about this device? So this is what is more important. What is the gain? Now, say, are we able to maintain same delay as that of CMOS structure? If I compare NAND 2 of pseudo NMOS and NAND 2 of CMOS, are the delays are matched? So I need to analyze on that. So how do? I can do it with RC delay modeling. Or I can even go with the linear delay modeling. So this time let us try it with the linear delay modeling. Okay. So now when we were sizing the device, okay, because it's very important. Okay, this discussion you have to remember, because you will get to see like different values. So far you had only one G value. Now you have so many. So GU means pull up logical effort. Okay, it's for up. That means when you are charging the output node to VDD, then what is the logical effort required? Okay, pull up. So GD means pull down. So it is for down. That means when NMOS devices are on, what is the logical effort needed? So this is for up. Okay, so G average is like average of these two values. Anyways, for time being, you can ignore average value. So it is like, say, when you want to give one single value, like we average it and give, because it's pull up, pull down every time, right? So that's why. So similarly, you can see the parasitic delay also. What is the delay when it is pull up? What is the delay when pull down? So now you may ask me a question: why didn't we do this exercise? Pull up, pull down. Two different pull up, pull down values for the regular CMOS circuit. Why we didn't do that is like you will get almost same. That's because, you know, you have matched to the unit size inverter with the ratio 2:1. Okay, when I do that in CMOS inverter, why I do it like 2:1 ratio? That's to make sure that charging time and the discharging time both are same. So that means if charging and discharging both are same, then delay involved during charging and delay involved while discharging both are same. So we didn't calculate, say, different pull up and pull down ratios. pull down logical efforts, okay, or a parasitic delay, because we assume it to be equal. And why did we do linear modeling? That we are going to tell you, like though we planned it to be equal, how it is like differing by some values, okay. So now it is a case that say CMOS inverter, if you neglect the 2:1 ratio and you randomly size it, neglecting that, then there also you are going to have different charging and discharge time, okay. That time while charging, what is the logical effort? That means how much delay is deferred by how much value, okay. While discharging, delay is deferred by how much value when compared to unit size CMOS inverter. That you have to calculate, okay. But we have taken that ideal condition that charging and discharging time will be equal. That's why we have calculated only one logical effort. Now this is a case when it comes to the pseudo NMOS structure. As you see, like while charging, it will be like always have one device, but while discharging, it will have multiple device. We have sized it according to the CMOS inverter, but now the reference is a pseudo NMOS inverter, okay. So now it is more likely that we may have unequal charging and discharge time. So now we are supposed to calculate what is the parasitic delay, what is the logical effort while charging and while discharging. That's why we have these two values, okay. Is that clear why we want to do? Any doubts?
Ma'am, GD value, how did they get calculated?
Yeah, that I'm going to tell. Don't worry. Calculation part.
Oh, fine.
Okay. Because if you directly see, you will not understand anything. Like you will be wondering how 30/9, how 18/9, all that, right? So it's very hard if you directly go with this. So what we do is like, for us, like while sizing or anything, for us like pull down was very important. Okay. So when we have a pull down, let us calculate the delay associated in pull up with respect to the pull down. Okay. Just because say if A has to pull down I amount of current, the current contribution from the PMOS is going to be I/3 if I maintain the sizing 1/4. Okay. If A has to pull down, that means NMOS inverter has to pull down I current from the output node. See, why I size it 4/3, that means it should pull down I amount of current. That's why, right? So if it has to pull down I amount of current, so it will, PMOS will charge
pull down 4I amount of current.
No, it's not like effectively how much current it will discharge. What is the effective current? It is I.
Discharge is I. Discharge is I, but
so
through NMOS it's 4I.
Yeah.
4I/3.
Sizing why I am doing 4/3. That's because effective discharge should be maintained at I. That's why, right?
Yeah. Correct.
So if I want to maintain effective discharge at I, the charging will happen as like I/3. Correct? During charging.
Correct, ma'am.
Correct. No. So now if PMOS is providing I/3 amount of current, that means I/3, if it has to charge to I amount of current, then it should work 3 times harder.
Correct.
Got the point? If it has to provide I amount of current, then it has to work 3 times harder when compared to NMOS. Got the point? Because if NMOS has to discharge I amount of current, okay, I/3 amount of current is provided by PMOS. So if PMOS is also providing I amount of current, then PMOS should work 3 times harder because I need I, right? So if I say the NMOS is discharging I amount of current, PMOS is charging I amount of current, then PMOS should work 3 times harder. So that means if I put it in this sense that if I want to maintain I current, okay, the effort given by a PMOS is 3 times more than that of NMOS. Do you agree with me or not? Effort given by PMOS is 3 times more than the NMOS. Yes or no?
You mean longer, right? Not harder. PMOS
Harder.
must work
Yes.
3 times longer and
Harder,
harder.
longer or harder, whatever.
Harder would mean that we want I by 3 to increase, but what we
Yes.
essentially want is the charge Q is equal to something.
See, it's like
So it's like if you have the current 1 by 3 times lesser, if you want.
I'm comparing. See, so logical effort is like I have to compare apples with apples only. I can't compare apples with oranges. Okay, so thing is like, see, when we did logical effort for a CMOS gates, so what we did is like, if you remember, you were asking me why we have to take this. I said like it has to provide same amount of current so that it can also drive as that. I mean, same amount of current as that of CMOS inverter. If you remember.
I remember.
Yeah, the same effect is like I want I amount of current. So if through PMOS, if I want to get I amount of current, PMOS should work 3 times harder. That means what? The time taken by a PMOS is 3 times more than that of NMOS. Correct?
Yes,
3 times harder.
I think harder
means
by
time.
harder you mean longer, right?
Longer,
like more
longer
amount of time.
Yes.
Yeah,
3
that
times
is the
long.
only clarification.
So if you down, if propagation delay is some X unit, but when PMOS is pulling up, then it is going to be 3x.
Yeah.
Got the point? So now in logical effort is like while pulling down, the effort given by NMOS is 3 times lesser than the effort given by a PMOS. Got the point? Logically also. So now, so when we are actually writing all these logical efforts, so how will we write is like, say, a PMOS is actually delivering around I by 3 amount of current. So if I want to make that current equated to I, then it has to wait 3 times more. That often, I mean, it will take 3 times longer that of NMOS. So when I look at the logical effort, say logical effort when it is pulling up is actually 3 times harder or longer than, I think here I can use harder the word because it has to deliver same current. Okay, so harder than that of NMOS. So pull down. So if I look at the propagation delay. So propagation delay when it is pulling up, like when it is charging, is actually 3 times more than the propagation delay when it is pulling down. Yeah, so this relation you have to remember. These two relations. Based on this, we can calculate. You calculate, it's very hard to calculate, okay, what is pull up, what is pull down and all. So you first calculate what is pull up. Calculate pull up. Calculate for pull up. So what is pull up? Logical effort. Then multiply by 3. You will get pull down. Okay. So similarly, parasitic delay, if you are calculating, calculate, pull down first. Now let us do that. Okay, let me go with the delay.
Why not the other way around? Like, is it not possible to do? Or
it is now it is like the other way around. If you are doing, then you can do. Here it is triple multi.
It's easier finding pull up, because you just have one MOSFET. I'm generalizing, not for the inverter only, but if you look at some other gates also.
So what I find is like pull down if I calculate is just multiply by 3, every time. So it will be easy.
Okay, we'll see in the next example.
Okay, anyways. So now what I'll do is like, so please calculate pull down propagation delay for this. Then we'll go to logical effort. Okay, inverter I'm looking at. What is propagation delay expression? See, of a gate divided by, are you there?
Yes, ma'am. P of the driver, P that is the loading of the driver, and P of the inverter.
Okay.
Yeah. C of the inverter.
So at this node, what is the P value? 6 by 3? Yeah? What is the P value? Propagation delay, I mean C out value. All propagation delay calculation, in a linear delay model. Okay, 6 by 3 divided by P for an inverter was 3, if you remember. So it was simply 6 by 9. Okay, so this I'm calculating while pull down. Okay, so this is what I'm doing. So this particular value 6 by 9, why I got is because of this. So this is a pull down. Okay, so now if I want to do pull up, it is simply 3 times of, okay, pull down. So 3 times of pull down is 6 by 9. So what do we have? 18 by 9. Got the point? Why we get this number? So we calculate same manner, however we calculated for CMOS circuits. The same way we'll calculate, but we'll make sure that that calculation is only for the pull down. Why I do pull down first? Because like my logic output logic is decided by the pull down network, not by pull up network. If this would have been a pseudo PMOS circuit, then I should have done it the opposite. Harsh. Then it would have been only with respect to pull up. Now it is pseudo NMOS circuit. Logic is decided by the NMOS structure, the pull down network. So I'll do the pull down delay first. I'll do pull down logical effort first. Then I'll shift to pull up.
Ma'am, so that's the only reason, ma'am, because
That's
it's an NMOS, we'll do
NMOS, yeah.
PD first.
Yeah, we'll do PD first.
Yeah, because if you were to find PU first, you will get the same result.
You will get anyways, but I feel this is more comfortable. Like you calculate down first, then multiply by 3. The job is done. Okay. So similarly, logical effort, let us see. We have to do down first, right? So I'm doing down. What is a logical effort? C in of a gate divided by C in of an inverter, right? So what is a gate C in? So I have to look at only this, only one, because this is not common, right? It is 4 by 3.
4 by 3 divided by 2.
3. What? C in of inverter is what?
2, ma'am. For the NMOS. Oh, sorry, 3. Sorry. Yeah.
So what do you have? Pull down is 4 by 9 now. Correct? So you have this number 4 by 9. So this is what is pull down. So what should be the pull up? 3 times higher than that. So 3 into 4 by 9, you get this value. Got the point? Who is having doubt? So this is your assignment, okay? You take NAND 2, NOR 2, right? Pull up, pull down for logical and propagation delay. So if you calculate in the same fashion, you will get all these numbers. You need not to by heart. I think class time is over. Yeah. Immediately another class. You are supposed to log in now.
Started, ma'am. Yes, ma'am.
I hope others you don't have any doubt. Kaushik?
No, ma'am.
No?
I'll have doubts in the next class.
Yeah. Srinath, any doubt?
No, ma'am.
No. Okay. So all of you please practice. Assignment is now NAND 2 and NOR 2. You have to write everything and come for next class. Okay? Done. Bye-bye, students.
Bye now.